day 1 of our STTP, that is digitally controlled power converter for industrial and renewable application phase 3. The second session will be conducted by National Infotech Surat, and I request Junaid sir to kindly introduce yourself as well as National Infotech, and then you can carry on to your session. So over to you, Junaid sir.
Thank you, sir. Thank you very much, Prashant sir, for introducing us. So, we are very much glad that SSPT Jalgaon has invited us to deliver this STTP, and we have been involved with SSPT since last few years in major activities like arranging STTPs and faculty development programs and students project-based learning also. So we are thankful to all the participants and also the Paresh sir, Pawar sir, Thakre sir, who have already helped us in the whenever we have visited there, and that contribution means a lot to us as a organization. And with that, we have already conducted two sessions earlier this year, respectively last month and in the October and November. So first week we have the power converters. We learned about the power development of power converter, and then in the second week we went in with the how to develop the electrical drives using this WAIJUNG block set. So now we are entering in the third week with the purpose of developing the renewable energy systems. Okay, so today, so this 5 days, Thakre sir and team has provided us the 5 days session, 5 days to provide our experience, what we have experienced in developing this renewable systems at our facilities. And so today's and so I'll give you the brief about how our session is going to be for the next few days. So first on today we will be learning the WAIJUNG block set, how we can configure this WAIJUNG block set, and then moving on to we are having the few basic exercises which are required for the development of this renewable energy systems. Okay. Then moving on to tomorrow, tomorrow we will be seeing the how to implement the MPPT algorithm for solar, that PNO algorithm, and then moving on to third day, we will be seeing the grid synchronization using PLL and FLL techniques. Then on the fourth day, implementation of PV inverter in the 2 stage we will be seeing, and concluding it with the PV statcom operation. So why am I giving this brief of 5 days? Because I like the participants to be ready about the these topics when they are conducted. Okay. So with that, I will start my today's session. Let me share my screen. So my screen is visible, right? Thakre sir.
Yes, now it is visible.
Okay. So first I will brief about the National Infotech and company. So we are basically three firms working together. So first is RAM Electromech, other is Power Tech Marketing, then National Infotech. Okay, so the RAM Electromech is a professional organization engaged in the field of electrical, automation, and power quality solution required for various plants, engineering, and process industries. And also it has a capability and experience in the capacity to design, engineer, manufacture a complete range of electrical and it is also providing the power quality solutions. Manager objective of this company is to provide high quality solutions and prompt services. As is an extended arm of renowned power solution companies catering to diverse requirements. Well, the voltage stabilizer and also manufacturing products, the voltage stabilizer, isolation transformers, which are unity uninterrupted power supplies, and APFC panels. Then there is us, National Infotech. We are working in the manufacturing the educational trainer kits and also the training courses like this. We
How?
sorry, anyone having some question? Query? Okay, so we are also having the arranging this training courses repeatedly, and then there is a industrial solution we also provide, and we are working in the field of power electronics, embedded system development, and custom industrial automations. So NITech has developed 100 plus products, and it is having a long list of clients in all over India. The client list includes IITs, NITs, government engineering colleges, and self-finance institutes, and L&T, and also and also all other companies. Okay. So moving on to this week's topics, renewable energy development. Okay. So in this renewable energy development, we will be seeing this many topics. How we can configure it with the WAIJUNG, this how we can program this STM32 controller with the WAIJUNG, and how we can implement the MPPT in this power using this DC-DC converters, implementation of FLL and PLL, which is required when you are interacting with the grid and you want to supply the power from the PV to grid. And PV inverter single stage and two stage. We will be seeing two stage only. Then we will see the PV statcom operation. That PV inverter works in a in providing the power to the grid, and as well as it will work as a series shunt compensator. Okay. So apart from this, we are having these many courses. So anyone interested in this kind of courses, like if you want to learn the simulation in the Matlab or PSIM, they can come to us, and we can arrange the batch for them to learn the specific required course skill they want to develop, like FPGA also. They want to learn the FPGA programming, the STM programming using CubeMX, using C programming, and TMS controllers, and then PCB designing, industrial automation if they want to learn. So these are the basic, these are the other courses available to us. So with that, I will conclude my introduction to company, and we will move on to the today's topic. So today we are going to see few exercises. So first is to generate a pulse of 1 kilohertz on PD12 pin and toggle LED for 1 second on PD13. Okay, so before moving on to this, all of you are aware about that. Many of you must have used this Matlab for simulation. Okay, so simulation. So the simulation, we know that we require the power GUI block whenever we are using this power component. Okay, so that power GUI block here is replaced with this target setup block. So before I explain this target setup block, I would like to clear more that whatever we are developing here right now in this environment, this Matlab environment, is in the view of that it will be reflected on our controller. Okay. So let's say you want to create some boost converter simulation. So you have one switch, inductor, diode, capacitor, and some load and DC source. Okay. So your power circuit includes this DC source, inductor, capacitor, diode, and switch, IGBT or MOSFET, and load. Okay. So that power GUI block controls this power GUI blocks controls the speed and everything of that power circuit components, and how this and what controls the and to run that boost converter we will require to give it the pulse of pulse of some frequency. Let's say 50 kilohertz frequency. So that for to generate the 50 kilohertz frequency you will need some control circuit. So you take this pulse generator. So this becomes your control circuit, and that all the other components becomes power circuit. Okay. So that power, so we develop this simulation in such a way that whenever we want to move on to the hardware, that we only have to replace that power component with an actual component. Are you getting? Hello, am I audible, right?
Yes, yes, yes. Sir, audible.
Yes,
Okay.
you're audible, sir.
Okay. Oh, Mr. Yugal, you are there too.
Hello, Janu sir.
Yes, hello. So this you must be learning it like third time, right?
I'm very much keen to learn this particular board, sir. I'm very much keen to learn.
Yeah, yeah. Thank you very much. So, so
Yes.
this power GUI block will be replaced by this target setup block. So let me show you the location you can get this.
Sir, your
Over
voice is continuously breaking, sir.
in view of all the participants. Okay, is it okay now?
Yeah, now it is okay, sir. Earlier it was breaking the voice.
Okay, okay. So let me show you the location where we can get this. So first of all, we will have to go to this Simulink library browser. Then we will go to this WAIJUNG block set. It will take some time. Okay. So in the WAIJUNG block set, STM32F4 controller. So we will have to go into this STM32F4 particularly. So what does the so the student this digital output block, they want to get this block, so they just simply type in here the digital output like this digital output, and they will search it out. And what this Simulink library does is of both this STM32F40, both of the it is able to give any of the block. So if you take this STM32F0 block, then it will not you cannot be able to configure it for the whatever your requirement is. Okay, so that in so you have to be very much particular in getting these blocks So STM32F4 target, then to on-chip peripherals. Then on-chip peripherals will have to get this. Before we get to this on-chip peripherals, let me show you this target setup block. Okay, I got a little bit off track. So this device configuration to go. We have this target setup block. Okay, and other blocks is you can get from on-chip peripherals like this ADC. We will be using this analog to digital converter, this AC digital to analog converter, which we'll be seeing the exercise of these two in today's session itself, and this IO, this digital input and output, then this timer we will be seeing too. Okay, so from the okay, so coming on to this target setup, there are few changes. I think Mr. Yugal can also say that what are the changes to be made in this target setup block. Mr. Yugal, can you?
Sir, we have to select the first MDK arm, then MCU we have to change. Then in programmer we need to change the ST link. So
Yes,
three
exactly.
things we need to change here.
Yes, exactly. Okay, right. So Mr. Yugal has explained it very well that we have to select first the MDK ARM compiler. So before you install the WAIJUNG on your system, you have to install this MDK Kale Vision software, and then you have to install the ST-Link utility software too. Which provides the driver information for our controller, and also then and after that you have to install this WAIJUNG using Matlab. Okay, so these three changes you have to select. This compiler you have to select MDK ARM. The MCU which we are using is STM32F407 VG LQFP 100 meg. Okay, so that we are using, and for the debugger and programmer we are using this ST-Link utility. Okay, so these are major three changes to be made in this target setup block. Okay, then this digital output. So we will get this digital output from where? The Simulink library, WAIJUNG block set, then the STM32F4 target, on-chip peripherals, and this is this IO, where you can get this digital output block. Okay, the digital output block we will get. So we want to generate 1 kilohertz pulse on this PD12 pin and 1 second per LED. This PD12 and PD13 pin also happen to be the same LEDs located on our controller. Okay. Okay, so let me show you some figure for that. Okay, so this is our NITech National Infotech made microcontroller motherboard. It is taking some time to open. Okay, let me again open it. Okay, now it is open. So let me show you this. This is the National Infotech made motherboard for the STM32. Okay, so these are the, you can locate this digital PD1, 2, 1, 12, 13, 14 and 15, 5 volt and ground. So this, if you see this PD15, 1 to 10, 11, 12, 13, 14, 15, our pins are also located on these LEDs. this PD1, you can see these are the all indicates the LEDs. Okay. So we'll be this LED will be blinking as per the rate we give this pulse generator. Okay. So first pulse we on the PD10 12 pin we will see the 1 kilohertz pulse, and the PD13 pins we will see the 1 second pulse. So we how to configure this digital output. So let me open it. So from that we will have to select whatever the port is. So we have seen in this that the D port is here. Okay, so this 1 to 10, 1, 2, 3, 4, 5, 6, 7, 8 pins of PD ports are terminated here. Okay, so for that we have to select. We will have to select this port D, and from that whatever the how many pin we are using right now is PD12 and 13 only. So that we have to select, and from that we can configure this PD12 pin and PD13 pin. So simply whatever the frequency pulse you will give to PD12 pin, it will give you the pulse of that at that pin. Okay. So the PD12 on the pulse generator, you will have to give the this amplitude you have to select. Amplitude we have selected 1. The period is number of samples. So how many samples will be there in one cycle? Okay, so we have taken 10. And what will be the pulse width of means what will be the duty cycle of your pulse? So we have kept 5. So out of 10 pulses, it will stay on for 5 pulses, and it will stay off for 5 pulses. Okay, so from that we have selected this sample time. So 10 samples in 10 samples in one cycle. So that means that we have to generate the 1 kilohertz frequency. So we will divide it by 1 kilohertz. So that will sample time. Okay, sorry, frequency will be divided by the number of samples. So that will give you your sample time. Okay, so 1 kilohertz pulse will be generated. Same way it will be this will be generating 1 second pulses. Okay, so hope you have cleared this exercise, and I will show you the video of this. Please someone of you notify me if the audio is audible or not. Is it audible?
No, slightly increase your volume.
Okay. I'll be turning off my camera because because of the bandwidth. Okay.
Of first exercise.
Is it audible now?
Exercise actually we have planned and programmed, and
Yes.
Okay.
Already we have discussed that at PD12 pin we are going to generate 1 kilohertz pulse, and we have set up this pulse generator according to that. And at PD13 we are going to generate one pulse which will toggle the LED at every 1 second. So 1 second on, 1 second off. So this program is we have downloaded in our controller kit. So in this controller kit we can see that this LED is toggling at every 1 second. So 1 second on, 1 second off. In similar way, in this card also, in the daughter card also, this LED is toggling. So this LED and this LED are connected at same pin. This LED is inherent part of this daughter card, and this we have connected using some peripheral. So this is all about PD13 pulse that we have generated here, PD13. Now we will see PD12. So that pulse, PD12 pulse, are terminated here. Here this port is there, GPO port. So this pin is there. So to see in the oscilloscope, first we need to put ground. So we will see ground from here. So this ground is taken. So we need to connect oscilloscope ground with the controller ground. This is the prior condition, necessary condition to observe the signal in there. Now at PD12 we will put the first channel. So now we can see here 50% duty cycle pulse is there. So we will see its frequency. So to measure the frequency, we will go for measurement. So here we can see that we should select the source. So source is first source, first channel. So we will select the source. Then what we need to measure. So here the type. There are many types of measurement parameters are there. So we will select the frequency. So when we add it, it will be added here. So our frequency of first signal is 1 kilohertz. It is according to our requirement and according to our code. So this is the 1 kilohertz pulse. Now here at PD13, now we will put the second channel. So now this pulse is not visible, you can see here, but actually this is coming at every 1 second. So if we increase this time per division, you see. So now I made time per division 500 millisecond per division. So you can see. So it is at every 1 second, it is off, 1 second on. 1 second off, 1 second on. So this is all about the GPO operation of STM32 controller and its program we have done using WAIJUNG blockset.
So hope this exercise was clear to everyone. Hello? Am I audible?
Yes, sir. Audible, sir.
Okay.
Yes.
So we will move on to the second exercise of today. So for the second exercise, we have this push button toggle LCD on off. Okay. So we will be configuring this. We will be using two of the peripherals, the digital output, and then again the digital input. So we will use the digital input for the giving a push button command, and we will turning on and off our and displaying the on and off status on our LCD at the same time. Okay. So for the same, we are having this again. We will have to use this target setup block. The target setup block, you all know that how to configure it. So and then we will have to use this digital output. So on the LED we will be also observing that it is if the command is on or off, and then this push button input command is there too. So this is the digital input. We have the same way we can configure how we have configured this digital output. The same way we can configure this digital input. So let me show you from where we can get this digital input and outputs. So same location as the STM32F4 target on chip peripherals, IO input and output. So you have to select this digital input. Okay, and from there we have to select this port D. Then port D we are having this PD7 button. So please try to find out where is the PD7 button located on here. Is anyone able to find out? Okay. Anyone able to locate where is the PD7 button? It is located here. Okay. So here is the PD7 button located. So this PD7 button we will be using as a push button command, and we will be turning on and off our this PD1 LED. Okay, this PD1 LED will turn on and off on the command of this PD7, and will at the same time we will also display this on off state on this alphanumerical LCD. So we will see how we can configure this alphanumeric LCD. Okay. So first we have cleared this digital input and output. So we have selected the push button input switch, which we want to use as a push button input command, and the output LED, on which LED we want to observe our output. Okay. So and for the next stage, we want to display it on the LCD. So for the LCD, we will have to get these three blocks: this character LCD setup, character LCD write, and volatile data storage. Okay, so let me show you first where we can get this character LCD setup. So character LCD setup is common for both STM32F40 and F4 controllers. So the WAIJUNG block set, you have to go to this hardware, then the character LCD. From there you can get this character LCD setup. Okay, and also LCD write too. And this volatile data storage, you can simply get it by searching in this search field, volatile data storage.
काम आहे.
Let's just skip it. It is taking more time, so you can get this from there. You can get it from there. Okay, so no need to look for that. So how you can get this the whatever data you want to display it on the LCD? For that you have to configure this character LCD setup block. So in the character LCD setup, you have the similar task as we have done in the target setup block you have to do. So first we have to select this module 1, then the interface you have to select this 4 bits interface, and the number of columns we are having 16 columns, 16 cross 2 LCD, so that's where you have to select the number of columns as 16. And GPIO type you have to select push pull, and control port is we are using B. So and register select pin is 11, read write pin is 10, enable pin is 2. So this pin selection you have to make sure that it is in the same order as this. Otherwise you won't be display your data won't be displaying on the LCD. If you are using this particular particular controller board. Okay. And the data pin you have to select this for D4, D5, D6, and D7. Okay, so give it a I'll keep it for a few moment, and you note it down, or whatever you want to take a screenshot or note down in your books. Or right. Okay, this is how you have to configure this LCD setup, and then you have to display it on. For displaying on the LCD, you will have to write it in the data this storage volatile data storage. So for that volatile data storage, you have to get this volatile data storage, and you have to give it some name. So we have right now we want to display on or off on the our LCD. So that's why we have named this storage as a on and off. Okay, so how many size it will store? So it's 16 byte it will store. Okay, initial values initial value, it will initially display off whenever the control is reset. Okay, so this and also storage type, we have to select string, as it will be displaying alphanumerical values. Okay, so that's why we have to keep it as a string. So whatever the data coming in this this data storage on and off, this character LCD write will display it on the LCD, write it on the display this LCD. So how we can write it? So you have to select the what data storage you want to get the data from, and you have to and this character LCD write has to display it on the LCD. So this is so here you have to select this string buffer on and off. Right now we are only having this one buffer. That's why it will take this on and off. Okay. So this zero, this CMD 0 and X position 0 and Y position 0. So the X position is for the row position, sorry, column, which column we want to display our data on. So you can select from 0 to 15, as the 16 cross 2 LCD is there available. So you can select from according to your need, whatever on which column you want to display. And Y position you can select from 0 to 1. If you want to display it on the first line, you have to select this Y position as 0. And if you want to display it on the second line, you have to select as 1. And the CMD command, Mr. Yugal, would you like to explain why we are using this CMD command and what should be in order to get the output? What will be the difference if we keep 0 or 1?
Sir, I forget, sir, actually.
Okay, no problem. No issue. So whenever you keep it as a 0, so this controller will this LCD write will not erase the uh, previous data, and it rather it will just overwrite it. Okay. So if you keep it as a 1, so it will erase the previous data and rewrite the new data. Okay, is it clear? Good. I hope it is clear. So this is how we can get this LCD configuration. And this is some new block, this debounce. This debounce block you can get it from this digital input and output section. Okay, so the debounce, from the debounce there are three modes: this is normal, single latch, single pulse, and toggle latch. So in the normal mode, what happens, for as long as you keep the uh, button pressed, it will change the state of it from 0 to 1. If the initial state is 0 and you press the button, whatever the button is, right now here we have kept this PD7 button. So if you keep pressing it, the PD7 button, then it will give you the pulse, and it will be on the giving you one till you release the button. Okay, and the single pulse. So the moment you will press the button, it will give you the pulse of only single pulse, no matter the duration, how much you have pressed it for. Okay, and the toggle latch is it will change its state from 0 to 1 at every command, and it will change it for its state from 1 to 0 as well. Okay. So right now we have changed the toggle latch. Okay, on this trigger subsystem, we have kept this trigger, so it will detect this rising edge of the pulse. So you know that the pulse here is having 0 line, and whenever I will press this PD7 button, it will become 1. So that rising edge, this block will detect, and it will be enabled. So what will happen when this block is enabled? So we have kept this printf in here. Okay, so this is a printf block. So this printf will store the data, whatever we put in here. So what we have put in here is on, and this on will be stored in the data volatile data storage naming on and off. Okay, so whenever this detect rising edge, it will this subsystem will enable, and this subsystem will enable then that on data. On will be stored in this volatile data storage, and then that same will be displayed by this LCD write. Okay, and the same way we are detecting the falling edge and we are displaying the off command. Okay, so let's move on to the our exercise video.
So in the previous exercise, in the experimentation, we have already. So in the previous exercise, in the experimentation, we have already seen this operation of digital in and digital output with this latch block, toggle latch debouncing block. So when we press this key PD7, here status will change from 0 to 1. When we press second time, that status will change from 1 to 0. And here we have kept two block that we already know that when rising edge is detected, it will go inside this. When a falling edge is detected, it will go here. So here we kept on in this buffer we have written on when rising edge is detected. When falling edge is detected, at that time in this buffer we have saved off. So on the key press, it will print on this LCD, on the LCD 1 and 0. It will print on and off. So that we will see in the experimentation. So here, same program is downloaded. So this is the key PD7. This is the PD15 LED which is connected with this, and this LCD will show the status of that LED. So when I press this, LEDs become on, that is PD15. Here by mistake it is misprinted PD1. It is not PD1, it is a misprint. So here it is a PD15. So the order of this printing is reverse. So just neglect it. So it is a PD15 pin. So it is on. So we can see that here printed in on LCD printed on. So if I press again, this LED is off. Here printing is happen off. So similar way we can program and we can write something on the LCD according to our need. But this is just an example how we are able to program this LCD as well as key as well as LED in this for this STM32 controller using this WAIJUNG block set. So one more thing is that here you are observing that when I press this, here off is printing from the third location. You see, this is first location is 0, 1, 2, and third. It is actually fourth block, but here it is 0, 1, 2, and 3. It is printing from third and in the first line. See, every time. So now we will go for a program that why this is happening, that we will see. No. So in the program here, this block we have already discussed. Then also let us repeat. So here X position is set. So this X position will show that from where it should start in the X position. So here 3 is written. So it will go from the fourth block. 3 plus 1 means fourth block of LCD. And this will show the line. So we have 16 cross 2. 2 means 2 row and 16 2 row and 16 columns. So this will show the address of the column and this will show the address of row. So 0 means first row, 1 means second row. If you change to 1, it will second row and fourth position according to this. So this is all about the LCD program using this WAIJUNG block set.
Hello. So hope this exercise is clear. Is it clear to everyone?
Yes, sir.
So we move now to our third exercise of today. Is basic PWM.
मोबाईलवर पण चालू काय लिंक आहे का ते मोबाईलवर थोडा आवाज बरा वाटतो मला कारण की याचा स्पीकर खराब आहे ना लॅपटॉपचा आवाज थोडा बरा
Someone has some issues?
नंबर ऑफ अमाउंट पर मंथ काही मराठी बोलणं का इंग्लिश
Hello.
टोटल ग्रँड फेलोशिप फेलोशिपसाठी हा
Hello. Someone's mic is on there.
अच्छा ये चालू आहे का
Okay. Hello. Please turn off your mic if you.
असेल ना त्यांच्याकडे त्यांनी तुम्हीच लावला ना इंग्लिश सरांनी सर मोबाईलवर करा ना ट्राय मोबाईल नाही त्यांचं लॉग इन वगैरे असेल ना आय डी हां तुमच्या मोबाईलमध्ये
So we'll move on to today's third exercise, which is basic PWM. So for the basic PWM, we will be using our to generate the PWM pulses of different duty cycles.
ईमेल की लिंक क्लिक करते ही बैक गया होगा
Yes, sir.
Participants are requested to kindly mute your mic.
हो ते क्लिक केलं की ओपन
Yes, sir.
झालं
Yes, sir.
Yes, there's someone's mic is on and
Participants are requested.
Oh, yes,
to
yes.
kindly mute
1
your
minute.
mic.
1 minute.
व्हिडिओ डॉक्युमेंट बघून घ्या हे आविष्कार बेनिफिट्स नवीन आले
Mahesh Patil. Hello, Mahesh Patil, please. Hello. Mahesh Patil, please mute your mic. Mahesh Patil.
विनर UGPG विनर्स व्हायला पाहिजे ते प्रयत्न केला
shall I continue?
ओपन करा ना मोबाईल मध्ये काय डेटा जाणार नाही डबल होणार नाही ना करा तर सही
You may start. Huh?
रेडी रेडी आहे का तुमचं काय कष्ट पाण्याला
I think you may be able to mute them as a host. I think the option will be available on your side.
मला परत 5:30 मीटिंग ऍड आहे ऑनलाईन नाही 4:30 साडेसहा हो हे महत्वाचं आहे सर याच्यासाठी ती दुसरी जास्त महत्वाची कोणची करताय का तुम्ही कशाची करताय
Sir,
Yes, sir.
you may continue, sir. Junaid,
Okay.
sir, you continue. You may continue.
So for the basic PWM timer, basic PWM, we are using this timer 4 right here. Okay, so the timer 4 we have to select, we have to give. You all know the where we can get this block is STM WAIJUNG block set 32F4 controller, and then on chip peripherals from we have to select this basic PWM block. Okay, so basic PWM, we have to select this timer 4 right here. We can you can select whatever the timer you want from available from this here. Okay, so we are right now selecting timer 4 and giving it as a frequency, so it is a 10 kilohertz. The polarity we have set is active high, and that I will describe what is the polarity active high and active low. And this is channel 1, we are using D12, D13, D14 and D15. So if you recall on the first exercise, we seen this PD12, PD13 and PD14 pin on available in this GPO. The same pin we will be using for the generation of the PWM pulses. Okay, so the same pins available for the GPO are all can be configured as a timer pin. Okay, but for the timer of let's say this is the timer, this PB7 is also happens to be on the timer. So if you select this PB7 and if you generate the pulse of 10 kilohertz or 50 kilohertz and you try to get the pulse out from here, so this PB7 pin won't be able to give you the pulse of the pulses because it is configured as a GP, general purpose input pin. Okay, so that is the care you have to take. Okay, so this is active high and active low. I will have to explain. Okay, so I will first open the paint for that. Okay. Okay, so this carrier wave is here. So the carrier wave is here. So and don't mind my drawing because I am drawing with the mouse. Okay, so this is the carrier wave, and this is our reference wave. So whenever I am selecting is an active high, okay, active high. At that time, when it will be giving us the pulse is reference greater than carrier. Okay, reference greater than carrier. So let's say this is the 20% duty cycle, and yeah, here is a reference is greater than carrier, so it will give the pulse at here. Okay, same same like this. Okay, so like this, it will give you the pulses. Okay, and when you keep this active low, so the reference it will give you the pulses when reference is less than the carrier wave. Okay, so when the reference is less than the carrier wave, so reference so let's you can see this reference right now here is the less than the carrier wave, so it will give you the pulse the 80% duty cycle at the same when you give the 20% duty cycle. Okay, so this is how it will this active high and active low will work. Okay, hope this is clear. So participants, I would like someone of you to give this input here that this is clear to everyone. Mr. Yugal, is it clear?
Yes, sir. Clear, sir.
Okay, so we will see the video of this access experiment.
Welcome to the demonstration of basic PWM timer operation of STM32 controller, and here this is the program for it using WAIJUNG block set. So as we have already discussed that we are going to use a 4-channel. So all 4 channels are given with a different duty cycle. So we can give duty cycle between 0 to 100. And as we have discussed that inside this block, some triangular generation is there. So that triangular will compare with this reference wave. And it will generate a corresponding PWM pulse at PD12, PD13, PD14, and PD15 pins. And the period or the switching frequency we are setting in this block. So here we are giving the PWM time period, so that we have kept 0.0001, that is corresponding to 10 kilowatts. So we will see experiment. So now here we can see that whatever pin of that timer, that is PD12, 13, 14, 15, it is terminated here with the buffer output. So here we are able to observe that PD12 is here, 13 is here, 14 is here, and 15 is here. So now using oscilloscope, digital oscilloscope, one by one the PWM pulse generated we will observe from PD12, 13, 14, and 15 one by one. So for that, let me connect a scope, first channel of the scope at PD12, second channel of the scope at PD13. So now these two we can observe from first channel and second channel. So PD12 we can observe at first channel, and PD13 output we can observe at a second channel. So now we will go for the start. So in the oscilloscope, the first channel output is taken from the PD12, and that we have set the 20% duty cycle, and the second channel is PD13, that we have set the 30% duty cycle, and switching frequency of this, that we have set 10 kilowatts. So for measurement it we have already taken in the measurement, so we can see that first signal switching frequency is 10 kilowatts. It's very stable, and 10 kilowatts output we are getting. So this is the switching frequency of first signal, and it is same as a second signal. Now duty cycle of first signal, that is this yellow signal, is 20%. So it is measured as a 20%. And the duty cycle of third signal is, the second channel is 30%, that is set from at PD30. Now we'll change the output of oscilloscope channel at PD14 and PD15. So now it is PD14 output is here, PD15 output at here. So here also we are able to observe that the 10 kilowatts frequency is there according to our program, and duty cycle of the signal at channel 1, that is coming from PD14, it is 40%, exactly as we have programmed. And the duty cycle at signal at PD15, which is coming at second channel, is 70%. It is according to our code, and we can observe that frequency is 10 kilowatts. So now we will check this for the higher switching frequency. So let's check for some 100 kilowatts PWM operation. So we are setting timing according to 100 kilowatts. Then we will apply it, and we will download the code. So when we press here, it will download the code. So wait for a while, it will be downloaded, and then we will see the output on the oscilloscope. So now it is downloaded. Now we will go for oscilloscope, and here, so PD13 and PD14 output we have connected, and here the frequency measurement is there. So here we are able to see that now the switching frequency is changed to 100 kilowatts, but the duty cycle is preserved like 40%, and the at PD15 70%. So PD15 and PD14 pulse we are taking out according to our code. The switching frequency change is happen, that change from 10 kilowatts to that is 100 kilowatts, and the duty cycle is same 40% and 70%. So I hope you are very much clear with the operation of PWM operation using basic timer program. Thank you.
So hope the exercise was basic PWM exercise was clear to everyone. Mr. Yugal?
Yes, sir. Sir, I have one question.
Yes. Yes.
Sir, in our Matlab, we are having the state flow methods, right? So, with the help of state flow algorithm, is it possible to operate this STM32, sir?
Actually, sir, we haven't not yet tried that state flow operation to implement it in the WAIJUNG. Okay. So,
Okay.
for giving you the better answer, first we will have to understand what your objective is with that state flow diagram, and then
Sir,
we will have to.
suppose I want to make a MPPT algorithm with the help of this state flow.
Yes, yes.
So, what is your opinion? Like a state flow,
Yeah.
we
The
will have the
MPPT
easy.
algorithm we have used in this implemented using this WAIJUNG.
Okay.
Tomorrow itself is an exercise of that.
Okay.
We can develop the code for algorithm of MPNO algorithm, which I already mentioned in the briefing.
Yes, sir. Yes, sir. I have seen that one.
So that
Sir,
we will, that we will
so
see tomorrow. So yeah, go ahead.
okay. So that means you haven't tried that state flow will work or not. That we need to see, na? That
Yeah,
मतलब ये काम करेगा.
yeah, we have to see if it is possible or not.
Sir, my second question is that suppose if we put the any variable knob, like suppose I want to change the duty cycle with the help of one particular knob,
Yes,
or
yes.
I want to change the switching frequency with the help of one particular knob, like we are having the knob facility
Yeah,
in our Matlab. So is it possible to get the such variation through this STM32?
yeah,
If I want
exactly.
to.
Yeah. Even also after the session, the exercise we will see the break. We are right now. We will take a break, small break, and
Okay.
and after that, whatever the exercise is there, that will clear your doubt on that.
Okay.
Okay.
Right, sir.
So, okay. So for the first session, I will conclude here, and we will take a small break, and we will continue at 3:45, and after that, we will see some few exercises there. Okay.
Okay, sir. Okay. Okay.
Exercise of digital output and interfacing with the keyboard and LCD, and also we have seen the one exercise of basic PWM using the timer. So now we will move further and see the advanced PWM timer, advanced PWM block, and how we can configure the timer to give us the both complementary pulses at the same time, and all the other features of that. So for that I will share my screen. Okay. So the advanced PWM block, you will have to get it from the same location as the basic PWM, WAIJUNG block set, TM32F4 target, then on-chip peripherals, then to timers. And then from the timers you have to get this advanced PWM block, and for the configuration of it, we will have to select for the advanced PWM. We have provided the two blocks on two timers are available. So naming timer 1 and timer 8. You can and see on the board on the right hand side lower corner, right hand lower corner, that timer 1 and timer 8 are available, which are denoted which are used for the advanced PWM. Okay, so these two blocks we can only use as a advanced PWM block. Okay, so this timer 1 we have selected, and the PWM period, which is also what is the switching frequency we want for our carrier. Okay, so this and the counter mode, which is the timer counter mode up. So in the timer counter mode up, so this will generate the carrier wave like this. This is a right aligned triangle, and if you set this timer counter mode down, then it will generate pulses like this left aligned triangle, and when it is centered, so it will generate a pulses like this. Okay, so this is how the uh, this this basic three changes, and this break option, and which will be explained in detail in the experimental video. Okay, and the output state you have to select. If you have seen this on the board, that this A8 B13 E11 B14 and A10 E B15. So whatever the pulse coming on the P8, the complement pulse of that pulse will be coming on from the PB13 pin. And for the same applies for the E11 and B14. The whatever pulse is on the E11, the complement of this E11 pulse will be on the PB14, and same way on this PA10 and PB10, PB6. Okay. So if you only want to use that this upper switches, let's say if you want to only get the pulse out from the PA8, and you want to keep the PB13 vacant, then you have to select this option of the PA8 output state enable. And if you want to select only want to get the pulse on the PB13 pin, then you have to select it output and state enable. And if you want to get the both pulses on both pins, and in that case you have to select this output and state enable. Okay, so this is the channel option. What is the polarity high and set we have to select. Okay, so this will be also explained in the video. Okay, and this the that time you can also give according to your IGBTs and MOSFET data sheet. So right now we have provided this 1 microsecond deadband. So that deadband is provided in order to overcome in order to avoid the shoot through fault. Okay, so the same pulses, the same switches of the the same switches of the single leg should not be turned at any instant simultaneously. Okay, so to avoid that, we are giving this giving it a dead time. Okay, so we will get this 20% duty cycle on the PA8 pin and 80% duty cycle on the PB13 pin. Same way, 60% duty cycle on E11 and 40% on PB14, and 50% on A10 and 50% on B15. So let's see the experimental video itself.
Welcome everyone for the demonstration of advanced timer program, and it's working. So here, as we programmed already, we have made a program this. So in that first we'll see that 8 signal at 8, which should be the 20% duty cycle. Pulse at E11, that should be the 60% duty cycle, and pulse 810 pin, that should be 90% duty cycle. So first we will observe this 3 pulse, and that pulse should be of a frequency of 10 kilohertz, which we have set here. So now after that we will observe the pulse A8 and B13 simultaneously. So we can observe that B13 should have a duty cycle of 80% and it should be exactly note of this. But if we have programmed, we have given some dead band, so that also we'll observe in that demonstration only that when A is turning off, after 1 microsecond only B13 will turn on. So there will be some 1 microsecond dead band. So that we will see. After that, here we have observed the B12 pin, that is for a break operation. So when we will connect a zero pulse, this is active low. So when we connect the ground at B12, at that time pulse generated from these pins will go to the its idle condition. Idle condition means this. So here we have said all pulse idle condition is reset. So all pulse will go to the zero when we connect a ground pin to B12. So now in this kit, as we have discussed earlier, that the pin related to timer 1, which we have programmed already, is terminated here. Pin related timer 8 is terminated here. So here we can see that our first channel output is coming at PA8 and PB13. These two are here, first and second. Then channel 2 is connected with PE11 and PB14, which is here. Then some ground pin is there. After the ground pin, here PA10 pin is there and PB15 pin is there. That is connected with channel 3 of advanced timer. So these are the 6 pin where we will get the output. So let me connect first PA8. That is the 20% duty cycle. Then let me connect PE11, that is a second channel output, that is 60% duty cycle, that should be 60% duty cycle. And third channel 3 output, that should be the 90% duty cycle. That 3 I have connected here. So channel 1, channel 2 and channel 3. So here first output will get at oscilloscope channel 1, second at oscilloscope channel 2 and third at oscilloscope channel 3. Now we'll go for oscilloscope and we will observe the output. So now here in oscilloscope, channel 1 is here, channel 2 is here, channel 3 is here. So channel 1 is coming from the timer pin PA8. Channel 2 is coming from timer pin E11 and channel 3 is coming from A10 pin. So here we are observing that this pulse is of duty cycle 20%, which is here. And all 3 signal are with a frequency of 10 kilohertz that we have programmed. And second channel, which is coming from E11 pin, its duty cycle is 60%. That is visible here. And third channel, its duty cycle is 90%. This is according to our code. So this is all about the output of channel 1, channel 2 and channel 3. Now we will see the A8 output, that is a channel 1 output, and the other pin output is B13. This is the CH1N channel, means note of this signal we will observe here. Now we are removing these 2 pulse, channel 2 and channel 3. Now we will observe the pulse from channel 1 pulse and its 1N pulse, means it's not pulse. These 2 pulse. So first is first channel of DSO, second is the fourth channel of DSO. So now we will go for digital oscilloscope. So here we can observe that the first pulse is with 20% duty cycle and fourth that we will take inside the measurement. So source 4 duty cycle, that is a reverse of that is 80% duty cycle. Now this pulse is not pulse of first channel. So this is the we can give to the inverter H1 higher IGBT, and this is to the lower IGBT or lower switch of one leg of inverter. But here some deadband also we have programmed that we will see here. So see, so when the second switch is turning off, After some time only the upper switch is turning on. So here we are able to see that in during this time both switch, upper switch and lower switch of same leg, 1 microsecond is there. That is the time per division. So per division 1 microsecond there. So this dead band is 1 microsecond. That is according to our program. So we are having here programmable dead band. So we are having a 3 channel and all channels are giving its note pulse. So similar to this. So we have now observed the output at 8, E11, A10 as well as the relation between A8 output and B13 output. So output at B13 was a note of A8 as well as between these two this dead band of 1 microsecond was there. And the frequency of signal was 10, that is according to our code. So these two things we have seen. Now we will see the other aspects. So here I have already discussed that the break operation we can do using B12. So here setting was that so enable with input active. So when we give this low pulse means ground pulse at ground or zero magnitude voltage at B12. When we connect the ground of a circuit at B12, at that time, all the pulses output coming from this, immediately it will turn off. Immediately it will turn off and it will go to the idle condition. So what is idle condition? Now ideal condition means this. So here it is written that we have said that so when idle condition is there, at that time pin should be reset. So we have said that all the output, all 6 output, 1, 2, 3, 4, 5, 6, all become 0 when we connect a ground with B12. So that we will see in experimentation. Now, so here that all pulse are coming. Now we are going to see the break operation. So to make it break or to turn off this pulse, what we will do is here in the controller circuit, ground is there here. So I have connected this connector at a ground. From ground, I will connect it to the PB12 pin, which is here. So when I put it in PB12, at that time you can observe in the oscilloscope that it will stop immediately the pulses, and that pulse will again start after clearance of fault or after reset of the controller. So now we'll see that when I connect, you can observe, please observe in the oscilloscope. When I So now you observe in the oscilloscope, when I connect the PB12 with the ground, the pulse will stop. You can see pulse is stopped. So if I remove again PB12, then also it remain off. Until unless I am not resetting the controller, pulse will not off. So let's see in the scan mode. So in the scan mode, if we see, so that pulse will off when I press, when I connect to the PB12. See, immediately it stopped. So this was the programming of advanced timer and its output. Thank you.
So is there any doubt in that this advanced timer, as PWM block?
No, sir.
Okay. Thank you, sir. Thank you, Yugal sir. So we will move further to the second exercise of this second session. So for that we have is ADC and interfacing with the LCD. So ADC, we all are aware that it converts the analog signals to the digital signal. Okay, so for the ADC, in our application, we'll be using it to get our output signal out to sense whatever the signals we have sensed, like voltage or current, whatever the signals we have sensed, we will convert it. We will convert it into the digital form and then we will give it to the controller, and we will see how we can calibrate that signal. Okay. So as before the break, Yugal sir was asking about how we can change the duty cycle with some nodes. Okay, so the same answer lies in this exercise. Okay, so for the configuring this ADC, we will have to get this ADC block. So we can get this ADC block. I think all of you are aware that WAIJUNG block set have 4 target, 1 chip peripherals, and this ADC. You have to get this regular ADC. So for the channel selection, you will have to select this uh, channel according to whatever the channels available on our board. You can see here. Okay, this A0, A1, A2, A3, C0, C1, C2, C3, and C4. These 9 channels are available on this motherboard. Okay, and the same channels are uh, terminated over here in order to, if you want to short this channel and vary it is connected through this potentiometer, and you can vary the resistance of it, and accordingly the voltage will be vary on this channel. Okay, so that we will see you will be able to see properly on the experiment video, where we have shown that this A1, A2, A3 represent this A0, A1, A2 channel. A4, A5, A6 represents A3, C0, and C1 channel, and A7, A8, A9 represent this C2, C3, and C4 channel. So if you want to vary the duty cycle with this, let's say this PA0 channel, so then you have to short this jumper. Then this variable resistor will be in the circuit, and you can vary the port by varying with using the port setter, and you can vary the voltage and that voltage will accordingly change your duty cycle. So that we will see, okay, in this exercise itself. So let's say these 2 channels AN0 and AN1 is selected here. So you can see this A0 and A1, these 2 channels are selected. Okay, so 3.3 by 4095 gain is given. Okay, so why this gain? I will explain it. Okay, so we are having a 12-bit ADC channel. Okay, so 12-bit means 4096 count. Okay, so whatever the signals we will give, the ADC will read it as as a count. Okay, so so that we will have to convert that count into the respected voltage. And what is the voltage is? So our board is working in the range of 0 to 3.3 volt. Okay, so our ADC will vary in the range of 0 to 4095 count. Okay, so it will be like this. Okay, this is 0 and this is 4095 count. Okay, total of 4096 count. Okay, so the respectively the voltage across here will be 0 to 3.3 volt. Okay, 0 to 3.3. So we have to convert this count into the range of this 3.3 volt, and from that we can convert this 3.3 volt into the whatever quantity we have sensed. Okay. Let's say you are sensing the voltage in the range of in the range of, let's say, 0 to 100. So when this signal will get the 3.3, your voltage is actually 100 volt, and that linearity will be maintained throughout. Okay, 0 to 100 volt. Let's say. But in this case, let's take a duty cycle. Yugal sir, are you getting?
Yes, sir.
Okay, so let's say this you are ultimately you are varying the count, but you are actually controlling your duty. Okay, you will vary the potentiometer provided on the board, and your count here, this count will be vary, and you will convert this count into the voltage, and then you will convert this voltage into the this duty cycle. Okay, for the 100 duty cycle, your count will be, let's say, this 4095, and for the 50% duty cycle, your count 50% duty cycle, your count will be 20448. Okay, is it clear?
Yes, sir.
So we are just simply just converting this count into the whatever the quantity we want. You can also skip this
Okay.
portion too, and directly convert it into the duty cycle. Okay.
Okay, sir.
So this conversion 3.3 volt is converted here, and here it is directly given to this printf LCD. So this data is it will give voltage and what are the counts at the ADC, and so that ADC count is stored in this line 1. Okay, line 1 storage, volatile data storage. So this will line 1, whatever the data is coming in this printf block, it will be storing this here, and this that's who will write the data, this character LCD write will display the whatever the data coming being stored in this line 1 data storage. Okay, so why the first order filter? So first order filter here it is for the 1 hertz frequency. So cutoff frequency is 1. So whatever the more the higher frequency greater than the 1 hertz, it will block. Okay, it's just simply low pass filter. Okay, the shift software low pass filter we can say. So we'll quickly move on to the exercise with experiment video of that.
Welcome to the demonstration of ADC programming of 80 of STM32 controller using WAIJUNG blockset. So these blocks are very familiar to us, and this also we have already seen that. So this is the block which is required to convert some analog data which is outside. In the hardware part it is there, that will take inside the controller. So in this ADC, as we already know that it take analog input between 0 to 3 volt, and that analog input is converted according to the ADC resolution. So that ADC inbuilt in this chip, on chip ADC, is having a resolution of 12 bit. So it can convert that data, analog data, in that range. So that range is 0 to 2 raised to 12 minus 1. So 2 raised to 12 is nothing but 4096. So 2 raised to 12 minus 1 means 4095. So if we apply 3.3 volt here as an input, it will convert here as a number 4096 or 4095. Similar way here also 4095 if we apply 3.3 volt. So now here we program this such that we will get the actual voltage value. So to get actual voltage value, we will divide first by 4095 and multiply by 3.3. This is the multiplication factor. So that value we will display in the LCD. And in the second channel, same voltage we will apply, and that voltage we will directly observe as a analog to digital conversion. So we will not convert or will not put any gain to convert back in the voltage. We will directly observe the converted value, that will be in the range of 0 to 2 raised to 12 minus 1, that is 0 to 4095. In between that will be there, that will be shown here. So let open it. So in the LCD, it will be written like the channel 1 equal to will be printed first, then 2.2F. That means that we will observe this value. This value means voltage value. So before this point, decimal point, two value it will show, and after that two value it will show. It meaning like that. And after some colon will be there. After colon, it will show the direct value. Direct value means the converted analog to digital value. That digital value between 0 to 4096 corresponding to applied voltage, it will show here. So this output is expected and in the experimentation. So now we will go for the experimentation where we will see the setup first. So in the demonstration, we can see that we have total 9 ADC channel. 1, 2, 3, 4, 5, 6, 7, 8, 9. One is a ground. The last one is a ground pin. So we are going to use this one and this one, first and second channel of ADC. So we'll give some input here. So if you want to give more input, you can give. But for this particular experiment, we are giving input at this channel and this channel. So this tube is also connected with here onboard pin. 1, 2, 3, 4, 5, 6, 7, 8, 9. So here total 9 other pins are there, which are isolated with each other and individually connected with this. So from top to bottom, these pins are connected directly with these pins. That is left side to right side here. So this pin, first pin is connected with the first pin of this. But here parallel you are seeing some lines are there. So here parallel also total 9 pins are there. Out of these, first 3 pins are sorted. 3 pins are sorted. First 3 pins are sorted. Internally, these pins are sorted. First 3 pins, second 3 pins, and third 3 pins. These pins are sorted with this potentiometer. The first potentiometer is connected with this first 3 pin. Second potentiometer is connected with this second 3 pins, and third potentiometer pins of this set of pins. So here the output of this potentiometer will go to all 3 this, but these 3 are okay. So if you want some output of this this potentiometer here and here, put first pin here, second pin here. So now we will sort with this. We'll see. Let me connect it and you can observe it. So I have given the output of this first set to the first pin here with the onboard potentiometer. Now to the second pin, I will sort using this jumper wire. So now here also you can easily observe that. So second also I have connected, means the set of 3 this side potentiometer pin is connected with first and second. That was terminated here. So now this 2 output of potentiometer, that will be between 0 to 3 volt. That will go
okay.
pin.
Adam വേണ്ടി ഒരു ഡേറ്റ്സ് ഒരുക്കിയിട്ടുണ്ട്. ഫ്രഷ് ഡേറ്റ്സ് അന്ന് വാങ്ങിച്ച ഡേറ്റ്സ് ഉണ്ട്. അതുപോലെ ഒരു ഫ്രഷ് ഡേറ്റ്സ് വാങ്ങിച്ചു വെച്ചിട്ടുണ്ട്. അതാണ് വേണ്ടി.
Channel 1 and channel 2 in the multimeter. So here I have connected this pin, multimeter pin.
അതെന്താ സംഭവിച്ചെന്ന് അറിയാവോ? നിങ്ങളുടെ ചേച്ചിയല്ലേ എന്നെ എല്ലാം ഒരുക്കി കാറിനകത്ത് കൊണ്ടുപോയി മറന്നുപോയി, ഇറങ്ങുന്ന സമയത്ത് മറന്നുപോയി എടുക്കാൻ.
I am reducing the voltage.
So പിന്നെ പറ്റുവാണെങ്കിൽ നാളെ കൊണ്ടുവരാം, ഇല്ല പറ്റുവാണെങ്കിൽ ടെസിക്ക് നമ്മുടെ അതം എടുത്ത് ഇങ്ങോട്ട് വരാൻ പറ്റുവാണെങ്കിൽ നമുക്ക് കൊടുക്കാം.
1.4, 1.5.
നാളെ
So it will change in the range of between 0 to.
ഇന്ന് ഡ്യൂട്ടിയിലാണ് ഇപ്പോ.
The range will change the range.
ആണ്.
So it can change up to 3.3. So this voltage we are seeing that we are applying inside at ADC pin. So now.
Okay, നാളെ കൊടുത്താ പോരെ?
But here it is
ശരിയാണ്. ഓക്കെ, അതും സുഖമായിട്ടിരിക്കുന്നല്ലേ?
That variable output from this port is
okay.
This 2 pin, channel 1 and channel 2. So channel 1 output we are showing here, and the channel 2 output we are showing directly. This is with a gain 3.3 divided by 4096, and this is without the gain. So here value will come between 0 to 4095, and here value will come, that is the actual voltage applied here. So now vary it. Now you can observe that 2.47 value is there. If I take it to the 3.3, let it take to the 3.3. So if we take it 3.3, this value will increase up to 4096. You see 4096 it is going. Okay, so now if we reduce it, it will linearly it will go down. It is 1.6, it will be almost half, that is 20 something. See, it is 20 something. So it is linearly, it is varying. Means the value applied in the volt, that volt inbuilt ADC is converting in the some number between 0 to 4096 according to its resolution. Its resolution is 12 bits. So 2 raised to 12, that is 4096. According to that, it is converting. And that value, again, we are giving some gain 3.3 divided by 4096. That is reconverting that value in the voltage. And that we are displaying inside. So this was the exercise for ADC and its programming we have seen. So I hope this is clear to you. Thank you.
So I think you guys you have now got the clarity about how you can vary the duty cycle with the potentiometer. Am I audible? Hello? Am I audible to everyone? Hello? Hello? Paresh sir, am I audible? Okay, okay. Thank you, ma'am. Thank you so much. Okay, so let's move on to the. I hope this exercise was clear to everyone. Miss Sonia, ma'am.
Yes, sir.
Okay, thank you, you guys. So moving on to our final exercise of today. So the final exercise includes this DAC, the digital to analog converter. So where what we are doing is the same way we are doing that one ADC we have configured, that ADC we have converted into the 3.3 volt, and that voltage will be given to the our DAC channel, and that DAC channel will display what is the value. We will also observe it on the DSO screen. Okay, same the some DC value we are getting, and some sine wave of 50 hertz we are getting out from the DAC, the DAC, and we will observe it on the DSO screen. So for the two DAC channels are available, is PA4 and PA5 channels. So you can locate it on the uh, right hand side of this ADC channels. Is PA4, PA5, and ground. Okay, so you can get this block from the same location. You must be aware by now that STA32 WAIJUNG set F4 target on chip peripherals and DAC. From you have to select this regular DAC block. Okay, and if you only want to use one channel, then you have to select this DAC1 only, and if you want to select get the output on both channels, then you have to select this to DAC2. Okay, so that's the change, and this 20 hertz pulse is given, 20 hertz sine is generated inside this controller, and it will it will be taken out by this DAC. The bias is also given of 1.5. So then why that bias is given? Can you specify why the bias is given in here? So the DAC will only give us the output in the range of 0 to 3 volt only. So that's why we will give the we don't want to get the output our signals in the giving us in the plus or minus negative value. So that's why we are giving the plus 1.5 bias. So our sign will be in the range of 0 to 3 volt. Okay. So we will see the exercise experiment video of it.
So welcome to the demonstration of DAC part and its programming and its experimental demonstration. So here in this file, actually we are taking two input in the DAC, digital to analog converter. So one input we are generating inside the controller, and one input we are giving from external hardware, that is our potentiometer, to the ADC. That ADC converting that value, some 0 to 3.3 value, into 4096, 0 to 4095 in between. That we are again converting in terms of voltage by multiplying this gain, and that value we are observing through DAC. So we are taking some data inside the controller, and some processing has been done, and that data we are taking out using DEC or DAC at one channel, A4 channel. And other signal, that is a sine wave signal. Now we will see the property of sine. So this sine signal, we have already discussed that its amplitude, peak to peak amplitude, is 3 volt. So its peak value is 1.5 into 2, that is a 3 volt. Bias is given is 1.5, so it will shift by 1.5. So this signal will be like that, 0 to, it will go 3, and 3 to again come to 0 and go to the again. So this signal will be positive signal, like shown here, like this. It will go to 1.5 to 3, 3 to 0, 0, so 3 to 1.5 again to 0, like this. It will be the between 0 to 3 volt, it will oscillate in the form of sine. And the frequency of that signal in the radian, it is given 314, that is nothing but 2 pi f. So 2 pi into f is 50, that will corresponding to 314 magnitude. So this was the sine generated internally, and this is the some analog signal we are given from outside, and we are taking inside, processing and taking out from the DEC. So, and here we have already set up that we will give the input. This show the which type of input we are giving. So here voltage we are giving. So range of voltage should be 0 to 3 volt. So this is also 0 to 3 volt. This is also 0 to 3 volt, that we have set here. So now we will go for experimentation. So here this ADC pin will get some magnitude 0 to 3 volt using this potentiometer. So this value will go inside the controller. Some gain is multiplied, 3.3 divided by 4095, and that value we are taking out using this DEC. So here DEC pin are terminated. That pin is A4 pin and A5 pin, PA4 and PA5 pin. And that two pin we have connected in with the oscilloscope using that this two probe. So one value you will get is a DC value that we are giving actually externally to inside, and inside to again outside. And second, we will get a sine of 50 Hertz frequency, as well as it will have a peak to peak magnitude 3 volt, and it has a DC shift or bias 1.5 volt. Now we will see the same thing, same output of this DEC in the oscilloscope. So here we are observing that output. This is the at channel 2, that is a sine output as we have programmed, and its bias is 1.5. Its peak to peak value is 3, and its frequency is 50. So it is according to our internal signal generated, and this is the value which is we have given from external output. So this is the first channel output, this is the second channel output. So now what we do is that whatever first input that was channel 1 of this DAC is given from the external, from this potentiometer. So if I change the potentiometer value, that is on here right now 1.37. If I change it, so same magnitude will be reflected here. So we can see that magnitude is changing there. So here 2, so here also it is changing 1 volt per division, so it is 2. So now further we will change it, let it make to 3. So if you make it 3, so here also it is coming 3. So like that we can change and we can observe the internal analog signal using the DAC. So I hope you are clear with the DAC. We are having a 2-channel of DAC, and this was the experimental demonstration of this program of DAC. Thank you.
So I hope this DAC exercise is also clear to everyone.
Yes, sir.
Okay, thank you, Yugal sir. And with that, we can conclude today's session. And hopefully, we have covered all the required exercise for the development of renewable energy systems. And from tomorrow, we will see the actual implementation in the MPPT algorithm and boost converter. Okay. So with that, I will conclude my today's session. But before I conclude, so I hope you have enjoyed this session. And similarly, from the next Monday, which is 21st December, so we are having a course on the embedded C programming of the same controller, 32 STM32F4 32-bit microcontroller, with using the STM Cube MX. Okay, so I will provide a link, registration link in the chat and comment section here, and whoever interested in that, please participate. Okay. Okay, sir.
Sir, thank you very much, sir.
Yes, sir.
Junaid, sir. So
Yes,
thank
sir.
you
Thank
very
you, sir.
much. So on behalf of SSBT College, I I would like to thanks National Infotech Surat, Viral sir and whole team for giving us a time. Thank you very much. Just announcement, please you join tomorrow at 10:45. So tomorrow the guest is Dr. Raghavan from IIT Gandhinagar, and he will speak on grid connected wind energy conversion system. Please do not miss tomorrow's session. Okay. So thank you very much, everyone. Please join tomorrow at 10:45. Feedback link is given in the chat box. Please use this link and put your attendance. Thank you very much, everyone. Everyone, do you have any question? Please, sorry, I forget it. Any question? Do you have any question?
Yeah, Jinesh sir, I having one question. Sir, is it
Yes, sir.
possible to
Yes.
have a model in simulation through this STM?
Sorry, I don't get your question properly.
Sir, model in loop is possible with STM32, sir?
Model?
Model in loop it is
Model
available with STM32?
actually, I'm not aware of that right now, so I'll have to
Okay,
check
okay,
it. Okay.
okay.
Model in loop, right?
Yes, sir. Suppose
Okay.
I mean to say, suppose if I change anything in the Matlab,
Yes, yes.
then same thing will be reflect on the board also.
Okay. Yeah, yeah. Yeah. No, no, that facility is not available on this WAIJUNG.
Okay, okay.
Yeah.
Any question?
Online debugging is available in that the course where just I have said that C programming code course. So in that you can learn that how we can do the online debugging. The whatever changes you make in the kernel environment, it will be reflected directly on the controller.
Okay, right, sir.
Thank you, Yugal, for active participation.
Thank you so much, sir.
Anyone? Okay. Appreciable. Anyone? Please. Do you have any question? Then we can conclude today's session. Junaid?
Yes, sir, we can conclude.
Okay, thank you very much, Junaid. Once again. Okay. Again, we'll see tomorrow at 10:45. Please join at 20:45 sharp. Okay. Thank you very much.
Thank you, everyone. Goodbye.